Hi, this is Xiaojie from City University of New York. It is my pleasure to give this presentation in CCGrid conference. The title of this paper is Energy Efficient for Computing Framework for Real-Time Video Processing. As it describes, we focus on energy saving, real-time processing applications, and fog computing. Before we go through the fog computing environment, let me first introduce the limitation of cloud-based solution for real-time video processing application. As we can see in this example, and devices they will capture raw videos and send video to the remote public cloud. Because of the non-distance between the data source and the cloud server, and also because of this unreliable internet backbone, the latency usually greater than 100 milliseconds. And also when it comes to high quality video frames, it will take even longer. So we can see that the cloud-based solutions, they cannot guarantee the real-time nature of the application. And what we have to do is to move the near cloud scale resources closer to the application. We say closer to the data source and to the end devices. So we can get rid of this non and unreliable data transmission. And that comes to the fog-based compute environment for the real-time video processing application. So in this example, end devices, they are sending their raw videos to the edge nodes through this short distance device to vehicle communication. The vehicle are working as the edge nodes, and they are equipped with some CPU and GPU resources. For this environment, where the management and optimization, they face multiple challenges in the full computing environment. The first one is the high transmission cost when sending the high quality video frames to the edge node for those energy constrained end devices. And this is a very good example. And this is a DJI Inspire 2 drone from their official website. It says that the maximum flight time is less than 30 minutes. So if we consider a non-ter and a real-time data transmission procedure, the energy consumption becomes a major problem and also a major bottleneck for the performance. Another challenge is the lack of cooperation among end devices when they are from different stakeholders in the resource computation. And here's another example. So the fire department in New York and the NYPD, and they belong to different departments, of course. So they are going to use different applications which help to speed up their rescue operations. So those applications, they have different features and they have different requirements, and they have their own purpose. So those applications, they belong to different departments. So if we consider the resource computation, lack of cooperation will lead to the inefficient use of the limited figure resources. Consider the computational unit and the radio unit. Well, another challenge comes to the application itself. So most complex video application require multi-stage, we say multi-jobs computation. Here we use a face recognition application as the example. The end device sends high quality video frame to the server, and the server will run the face detection algorithm, and it contains 3 jobs: face detection, feature encoding, face matching. So if we consider the application requirements and also the energy of the devices, joint optimization of energy efficiency and data satisfaction is not easy. Well, to make a conclusion, we know that for high quality radio and real-time processing, the transmission cost may overwhelm the energy saving from offloading. And this is what we don't want, because we want to utilize the fog computing in order to save energy. An alternate approach is the partial offloading. Sometimes it makes more sense to locally compute and transmit the intermediate data rather than transmit the raw data. So for example here, this flying computer, which is Skydio 2, it has NVIDIA Jackson Tech 2 for the local computation. So if we have this kind of devices, instead of sending the raw data, which is very large, to the edge node, we can do some pre-processing, and we can run some lightweight algorithms to generate some smaller intermediate data, and it saves considerable data transmission cost. So in this paper, we propose the intelligence task partition, and we use this partition to reduce the energy spent on the data transmission by running certain lightweight pre-processing jobs on the devices. For example, here, the device runs the first 3 jobs and sends the intermediate data to the server. The server runs the rest of the job once receive the intermediate data. The challenge is to find, for each application, is to find how we're going to partition the jobs, so we can minimize the device energy consumption, and in the meantime, make sure that we are not violating the real-time latency requirement. So again, we are going to use this face recognition as the example. So from the jobs in this face recognition application, we know that the first job, face detection, is lightweight compared to the feature encoding and face matching. So that means if we want to reduce the energy consumption on the data transmission, we should let the device run the face detection. That means the end device only needs to transmit the detected facial images, which are usually in small size. So this method can greatly reduce the transmission cost. We have a large original input, and now we only have to transmit the small intermediate and facial images. Also, when consider there are multiple real-time applications and multiple servers, and then it becomes a multi-device, multi-server offloading problem. We have to consider diverse energy and the compute capacity of the devices, and also different radio conditions. On the other hand, applications they have diverse job features and requirements. And we may also consider heterogeneous edge node. So these together constitute a complex offloading problem. In this work, we first formulate a mixed integer nonlinear program, and we propose the effects framework. So our framework considers the following functionalities. First, task partition for each application, server selection for each device, and also joins radio and computational resource allocation. To solve the proposed problem, the framework first divides the original optimization problem into 2 subproblems. The first one called CRA, the centralized resource allocation, is generates a centralized optimization problem for each server to minimize the overall energy consumption of all the offloaded tasks. So it stands from the perspective of the server. Another subproblem called DSM, distributed strategy making, which is a distributed game, to select the best offloading strategy to minimize the individual energy consumption. So the second one is a multi-device and a multi-server toss of the gain, and it's from the perspective of the device. The solution is obtained by alternatively performing the two subproblems until convergence. This gives the logic diagram of the effects framework, and the framework employs the Hepler processes that help the devices to make offloading decisions instead of letting the device itself running optimization algorithm, which is energy consuming. The framework has three major components: the application partition and toss offloading, and the resource allocation, and also a centralized unified resource broker (URB) that controls the communication between all the components. We implement a prototype with Apache Store. Apache Store is a distributed stream processing computation platform, and the major roles are in both zookeeper and supervisor. The input, like the brain of the framework, is around the effects algorithms and also the task to supervisor scheduler. The zookeeper is used for the registration and correlation. So in this prototype, both the servers and the devices are registered at the supervisor plot. The difference is that the working process of the device only serves the device itself. The work process of the server are going to be used for all the applications from all the devices. We generate 6 heterogeneous applications based on 2 jobs with different configurations, except the application 6, which only has 1 job. So the first job is a Lucene PNG compression algorithm with different image quality and options. The second one is the well-known Yellow V3, an objection detection algorithm with different frame resolution. So with different configuration, the computation complexity of the jobs will be different, as shown in these diverse job features. So first, we can see that the detection algorithm is much heavier than the PNG compression. And also the higher the resolution and the complexity of the detection algorithms becomes more complicated. It also shows that the compression algorithm can effectively reduce the raw image set, as we show in this figure. We create 4 cases, and each of them has different amounts of radio resources in terms of number of subchannels. In case 3 and 4, we use fair CPU allocation for the comparison, where the CPU resources are evenly allocated to the offloaded task without considering the task deadline. In case 1 and case 2, we follow the effects framework algorithm. For the results, in case 1, when the system has enough radio resources, say 48 subchannels, all applications select for offloading. That means both jobs are running on the server because the transmission cost is very small. In case 2, under limited radio resources, say 15 subchannels, all applications except application 6 will do the partial offloading because application 6 only has 1 job. It cannot do partial offloading to reduce the data transmission cost. And also, this application 6 will occupy most of the radio resources. Well, in case 3 and case 4, we can see similar behavior when the amount of radio resources changes. Especially in case 4, we can see that application 5 selects local computation because the transmission cost is too high and it overweighs the benefits of energy saving from offloading. In this figure, it shows the comparisons with the fair CPU allocation strategy. Compared to the fair allocation, the effects framework saves 40% on the total energy consumption in sufficient radio resource scenarios. And it saves 16% when it comes to the limited radio resource scenarios. We can see that the availability of the edge resources, especially the subchannels in those cases, they play a significant role in task offloading decision making. I mean, whether the device are going to select the full offloading or partial offloading or local computation. We also evaluate the system performance against a larger size of application and edge servers using the simulation parameters. From both cases, the effects algorithms constantly saves more energy than the fair and the proportional resource allocation. So in this figure, those numbers indicate the minimal requirements for the resources that the offloading becomes benefit compared to the local computation. As last we studied the Lash equilibrium of the proposed task offloading game, we found that the algorithm terminates after a few iterations, in this example between 14 to 15. And after that, no device can further reduce its energy consumption by unilaterally changing its own strategy. That means all devices reach the Lash equilibrium. In the future work, we will consider arbitrary application structure. So in this work, we only consider the linear topology of the application. And also we try to apply deep reinforcement learning approaches to further improve the system performance and to improve the convergence speed. Thank you. And any question?